Hi all, today we will discuss about floating point multiplication and floating point division operation. So before going to multiplication and division, it's really important to understand the representation floating point for a real number. So the floating point representation for a real number, let's take an example of 15.250 is a number, and all of you know that 15 can be represented in the form of 1111. How? If you apply the weighted code 8421, if you say all 1, so the 8 plus 4 plus 2 plus 1 becomes 15. So this is how you got 4 ones. The binary equivalent of 15 becomes 4 ones followed by 0.250. How to convert the decimal fraction 0.25 into binary fraction? Just multiply with 2. 0.500 multiplied by 2, 1.00, so that becomes 0.1. See the decimal, just to confirmation, after decimal point you keep 2 power minus 1 and 2 power minus 2. 2 power minus 2 into 1 by 4. 2 power minus 2 into 1 means 1 by 4 into 1 is nothing but 0.25. So this is the floating point representation for a real number. And real number, remember, the real number contains both integer part and fractional part. So 111.01 is the binary equivalent for the decimal value 15.250. Now, how to represent this, how to store this real number? So this is an example of a real number, and how to store this in computer memory in the form of floating point representation. Means convert this number, see, you shifted the binary point to 3 positions here. Since you shifted the binary point in 3 positions, to compensate the value, you should multiply with 2 power 3. So this is the position of the binary point. So 2 power 3 is nothing but exponent, and this is the fractional part, or you can call it as mantissa. So the mantissa value would be something like 1.11101 into 2 power 3. So 3 has to be represented. 3 is called exponent and this part is called mantissa. So when you convert 3, it becomes 1 1. Moreover, it is as plus 3, so you will add 0 here. This part is called exponent, this part is called mantissa, and the mantissa becomes 11101. So this is the fixed point representation for the decimal number 15.250. So everyone should clear about this. Everyone should be clear about this fixed floating point multiplication. So the floating point, as the name says, the position of the binary point is floated one, is not fixed one. So it is really important to mention where the binary point is. And remember, we are not mentioning the leading one. As all of you know, this leading one is assumed to be the default one. So when someone interprets 110 111 01, this assumed to be mantissa, this assumed to be exponent, and this assumed to be the sign bit. First take the mantissa and add as a fractional part, and take this value 3, moreover it is 0 plus 3. So if you to remove this one, you need to shift the binary point to 3 positions. So 111 1.01, that is nothing but the original number 15.250. This is the interpretation of a floating point number. So in this, let's assume we have two floating point numbers, and it is important to understand how multiplication and division has been carried out for two floating point numbers. Let's take a decimal example. 2 into 10 power 3, this is one number, multiplied by 25 into 10 power minus 6. So what you do here, the multiplication of floating point numbers, the logic is quite simple. Take the exponents and add them, minus 6 plus 3, 10 power, and multiply the matrices directly. So the result would be 50 into 10 power minus 3. The reason behind this is that if you multiply 10 power 2 in 10 power 3, it is nothing but 10 power, you have to add exponents 2 plus 3. So if you remember this basic formula, it is quite easy to understand the multiplication of two floating point numbers. So the multiplication of two floating point numbers requires that uh, we multiply the mantissas and add exponents. The logic is simple. You just multiply the mantissas and add the exponents. No comparison of exponents or alignment of mantissa is necessary. Remember, as we have done with floating point addition and subtraction, no need to compare the exponent values, just, and also no need to align the mantissa. These 2 points are required. Only two basic steps. Step 1 is add exponents, and step 2 is multiply the mantissas. This is the simple procedure that we follow for floating point multiplication. The multiplication of the mantissa is performed same as fixed point to provide double precision product. So the multiplying the mantissas is just like same as fixed point to provide double precision. So the mantissas here assumed to be two fixed point integers. Multiplication algorithm can be subdivided into four parts. One is again check for zeros, as we have done with the floating point addition and subtraction. It is really important to see whether any one of the operand value is 0 before proceeding further. Next, second step is add exponents without looking at the without no need to compare the exponents, just add the component exponents directly and multiply the mantissa. Multiplying mantissa is again a fixed point multiplication. Either you can follow Booth multiplication algorithm or the Booth multiplication algorithm or the normal multiplication algorithm that we will discuss. And next, normalize the product. Make sure that the most significant normalizing means making sure that the most significant bit or MSB of the mantissa should be a non-zero digit. So this procedure, floating point multiplication, is just like fixed point multiplication, but before that you just add the exponents. That's it. The rest of the procedure is same, and of course the fourth step, normalizing, has to be done because it is for floating point representation. So the procedure is quite simple. Multiplicand is in BR register, multiplier is in QR register, and here you see whether it contains any 0. So first you are verifying whether BR is equals to 0. If the BR value is equals to 0, no need to verify AC value. You can directly, any number multiplied with 0 becomes 0. If BR is not is equals to 0, then go for check QR. Again, if QR is 0, then the result would be 0. If the QR is not is equals to 0, then what is the step you need to proceed further? How you need to proceed further? Add the mantissas and store in the result. So this logic is for check for 0, step 1. Next step, after checking for 0, ensuring that none of the operands are 0, then we proceed to second step. Second step is directly just you add the exponents. So just add the exponent of exponent a plus b and store in somewhere. Remember, the small letters indicates the exponent values, so we are just adding the exponent of BR register and the exponent of the floating point number stored in QR register, assuming that their exponent values are A and B. This is the second step, add exponents. Next, the third step would be multiply the mantissas. Third step would be multiply mantissa. So how you do multiplication? I'll just repeat the procedure once again. So in case of fixed point numbers, you do multiplication. Remember, multiplication is the uh, multiplication of two fixed point numbers. Multiplication of two fixed point numbers again is the repetitive step of, you need to perform two steps. Right shift is one operation, and second one, add multiplicand to the partial product. Right shift partial product is the first step, and second step would be add the multiplicand to the partial product if the bit of the multiplier is 1. So let me repeat the process for a simple case. So if I have 1011 and which is required to multiply it by 1100. So assumed to be a multiplicand, this assumed to be a multiplier. So here what you do, multiply it, check the multiplier bit. If it is 0, you just need not to do anything, just right shift, doesn't make any sense. If it is 0, again don't do anything, right shift. If it is a 1, add multiplicand. Add multiplicand to the partial product, you get the result, and again you get 0 0 1 1 0 1, and this is the partial product. Again you are verifying this is 1, so right shift by one position, 0 1 0 1 1 double 0. Since it is 1, add the multiplicand 1 0 1 1, then you would get the result. The procedure is quite simple. Check the multiplier bit, LSB of the multiplier. If the LSB of the multiplier is, if the LSB position of the multiplier is 0, just right shift the partial product and do a right shift of the multiplier so that the LSB points to this second next bit. If the LSB position of the partial product is 1, then you do the right shift and add the multiplicand to the partial product. Remember, this is the logic we followed for multiplying a fixed point numbers. And finally you need to align the mantissa, no, then you need to normalize the result. Normalize means shift the result to the left until you get one non-zero digit in the MSB position. So this is the called normalizing the product. So let me repeat the process. The process is, first check for zeros. Second step is add exponents directly without looking at them, without comparing them, and then multiply the mantissas using a fixed point multiplication procedure which I explained now. And the final is normalize the result to get a non-zero digit at MSB position of the resultant product of, that is product of mantissas. This is the simple procedure that we follow for multiplication of floating point numbers. So let me repeat the process once again. First, check for zeros. Second one is add exponents. Third one, multiply the mantissas by just following the algorithm for fixed point multiplication. Remember, we have two procedures, normal multiplication which are in signed magnitude representation, which we discussed. In that you will verify the LSB of the multiplier. If it is a 0, then do a right shift. If it is a 1, then do right shift and add the multiplicand to the partial product. Remember, in case of Booth's algorithm, you will verify two digits of the multiplier, and the three possibilities can be 1 0, 0 1 and 1 1. If it is 0 1, then do a right shift, add and right shift. If it is 1 0, first right shift, again right shift and add. If it is 1 1, right shift, add, and again right shift and add. So the Booth multiplication algorithm is fast. So the Booth multiplication algorithm is somewhat faster when compared with normal multiplication algorithm for signed magnitude numbers. So this is the procedure for multiplying the matrices, and the next step would be uh, normalize the resultant value of resultant that we get by multiplying those two matrices. Remember, normalizing means just we have to make sure that the MSB position of the resultant matrices should be a non-zero digit. Next we look at the division, floating point division for multiplicate two floating point numbers. The floating point division requires that the exponents be subtracted and the mantissa divided. So this is the quite opposite procedure. Before that, let us discuss 50 multiplied by 10 power 3 and 25 multiplied by 10 power 2. So first you subtract the matrices. 3 minus 2 is equals to 1, so the 10 power 1. Then you follow the division of fixed point numbers. The same procedure, division of the fixed point numbers. So check for zeros, and second one subtract, check for zeros, initialize the registers and evaluate the sign, align the dividend, subtract the exponents, and divide the matrices. So these are the four basic steps for division algorithm. Check for zeros, this is called dividend, this is called divisor. If the dividend is 0, then the result, irrespective of the divisor value, the result would be 0. But if the divisor is 0, the resultant would be infinite, undefined. So it is very important to check whether the divisor value should never be 0. Otherwise, in a programming language, while we do a programming or when you write a program, you may get an exception called divide by 0 exception. So we should make sure that divisor should never be a 0. And if the dividend is 0, irrespective of verifying, no need to verify the divisor value, straight away the algorithm stops here and the value would be 0. The result of the floating point division would be 0 in this case. That is the first step, check for zeros. Second step, initialize the registers and evaluate the sign. Of course, the division, you need to evaluate the sign and align the dividend. This is the quite interesting step. You need to align the dividend so that you get MSB. Align the dividend means you need to make sure that the MSB position of the dividend becomes a non-zero digit, so that and also you should ensure that there are more number of bits in the dividend when compared with divisor. So it may be possible that the dividend can have less number of bits in case of proper fraction. like 25 into 10 power 3 divided by 50 into 10 power 2. So you can't directly subtract and apply division because the number of bits in the dividend or the value of the dividend is smaller than divisor. So here you require to align the dividend such that the value will be greater than divisor. How? By converting this into 250 into 10 power 2. Now you align the dividend. Now its mantissa value become 250, which is greater than 50. The same thing you have to do in binary. Just see that the number of bits in the divisor, if the number of bits in the dividend and division are same or not. If the number of bits in the dividend is greater than the number of bits in the divisor, no need to do align the dividend. But if the number of bits in the dividend and divisor both are same, then you may require to align the dividend by shifting the dividend value to the left so that the value will become greater than divisor. So this is the logic behind doing the third step, align the dividend. And after that the procedure is quite simple. You just see uh, subtract the exponents. Subtract the exponents means 10 power, in this case 10 power 2 by 10 power 2, 2 minus 2 0, 10 power 0 becomes 1. So indirectly these get cancelled and the result would be 5 when you apply fixed point division. Remember, fixed point division is the repetitive process of compare, shift right and subtract. Here what is meant by compare means compare the value of the dividend, number of bits in the dividend to the divisor, because the dividend should always more number of bits, and stop the procedure once you reach the number of bits in the dividend becomes lesser than the divisor. Then that becomes the remainder, where that is the point where you need to stop the division algorithm. So this is the procedure for divide the mantissa. This is the fifth step. Now let's see the flow chart for floating point division. So in this case, the dividend is in AC register, divisor is in BR register. First, check for zeros. If the BR, the divisor is 0, then you get divide by overflow exception, because first you are verifying the divisor value. If the divisor value should never be 0. If it is 0, then you directly subtract the value. You can straight away say that raise an exception, divide by 0 exception will get raised. If the divisor is not is equals to 0, proceed further and see now the dividend value is 0. If the dividend value is 0, then the result would be again a 0 and stop the procedure. And continue when none of the values are 0. So if the algorithm or flowchart reaches this step means you verified both dividend and divisor value and confirmed that none of them are 0. Now you verify the magnitude, the sign bit, and now initialize the sequence counter to n-1, because this is the process where you need to stop Now this procedure is much similar like doing fixed point division. You subtract the dividend minus divisor and see the you got any n carry. If you get an n carry, that means a is greater than b. If you if you didn't get any n carry, that means it is 0, then a is less than b. When a is less than b, you just add. When a is greater than b, add and do the right shift and increment the value. Similarly, follow the procedure for exponent values. And next, you divide the magnitudes of the mantisas. Just to here, you are ensuring that you are aligning the mantissa, aligning the dividend. Third step. And next, fourth step, you just follow the division procedure for fixed point numbers. Let me repeat the process. First, you compare the number of bits in the dividend with the number of bits in the divisor. If the number of bits in the dividend are greater than the number of bits in the divisor, straight away you subtract the divisor value from the dividend from the selected bits of the dividend. If the number of bits in the dividend are lesser than the divisor, then you just adjust the shift, perform shift operation so that the value would becomes greater and repeat the procedure. So this is the procedure for fixed point division where you just apply it and finally normalize the result. Here you are subtracting the exponent as well. So this is the procedure for doing the floating point division. Next we enter, this completes the floating point multiplication and division rule. Next we follow the third unit, that is computer memory system. This whole chapter speaks about the memory organization, how memory is organized in a computers, and what are the different types of memories, and what are the characteristics of those memories, and what is the reason behind having different memory elements in the computer. So first we'll see the important point. All of you know that all of you studied in the block diagram of a digital computer that when the user enters the data using any of the input devices, the data the user can enter the data or instructions. And all of you know that when the developer writes a program, basically he's writing a group of instructions, and all these group of instructions and data is going to be stored in secondary storage device or secondary memory. And the reason why it goes and stores in secondary memory means secondary storage, as we discussed, is a large memory when compared with the primary memory. And the secondary memory has also called auxiliary memory. The capacity of the secondary memory is larger, and also the data that is going to be stored in the secondary memory is permanent. But the characteristic of the secondary memory is that it can't directly communicates with CU and ALU. So for that we have another memory device called primary memory or main memory. The capacity of the main memory is comparatively less, but the speed of the main memory is fast when you compare with the secondary memory because it requires to interact with CU and ALU. So We'll discuss some differences between the primary memory and secondary memory. The first point is that the primary memory is also called main memory. The secondary memory is also called auxiliary memory. So the primary memory is also called auxiliary memory. The primary memory is also called the main memory. The secondary memory is also called auxiliary memory. So the primary memory is temporary. That means when the power goes off, when you switch off your system, whatever the data that has been stored in the primary is erased, but the secondary memory is permanent. This is from storage point of view. So the primary memory, whatever the data that is stored in the primary memory is a temporary one, but this data that is stored in secondary memory is a permanent when you compare with primary memory. The second difference is that the primary memory is directly accessible by processor or CPU. The secondary memory is not directly accessible by the CPU. So let me recollect simple accumulators device where we have a storage unit, secondary memory, primary memory, and this is data processing unit CU and ALU. So the primary memory directly communicates with CU and ALU, but secondary memory cannot directly communicate. The reason is the speed of the secondary memory is very much slow when compared with the CU and ALU. Further, we have the speed memory called primary memory. So the primary memory is directly accessible to or accessible by processor. Remember the word processor. Processor is nothing but a combination of control unit, ALU, and some registers. These three combinations are also called processor. So the primary memory is directly accessible by the processor. Secondary memory is not directly accessible by CPU. Why? Because the speed of the secondary memory is very low when you compare with primary memory. This is the second difference. Third difference is that the nature of parts of the primary memory varies. It's like RAM, random access memory, volatile in nature, ROM, read only memory, non volatile. So the primary memory example for primary memory is RAM, random access memory, which is volatile, where the data array will be erased once the power goes off. And in case of secondary memory, it is always a non-volatile in nature, that is permanent. But of course, in primary memory also there is some non-volatile, a special type of memory called read-only memory, which is non-volatile. This is especially used for dedicated electronic devices such as washing machine or refrigerator, which has ROM, read-only memory. Here this washing machine or some electronic devices are configured or programmed to execute a same task repeatedly. So in this case, the memory should be non-volatile. So this is about the nature of the primary memory with respect to volatility. Remember, volatility means the data is erased. Next, the fourth difference is that primary memory devices are more expensive than secondary storage devices. Primary memory devices are more expensive than secondary storage devices because they are fast, they take less memory, less space. Next, secondary memory devices are less expensive when compared to primary memory devices. Example for secondary memory devices are your external hard disk or internal hard disk, or your USB drive, USB or pen drive, or your CDs, compact disc or DVDs, digital versatile disk. All these are examples of secondary storage devices where the data is stored permanently, but the speed is very low when you read the data from these external devices. And the fifth difference is that the memory devices used for primary memory, the memory devices used for the primary memory are semiconductor memories. Semiconductor memory means they take very less space, but the speed is high, but they won't, they are stateless devices, semiconductor devices once the power goes off. And the secondary memory devices are magnetic and optical memories. Magnetic means they use some magnetic tape, or they follow the optical methodology to store the data in the memory devices. The goal is the data should be stored permanently. For that, we use magnetic and optical memories. So, this is the fifth difference between the primary memory and secondary memory. Next, the sixth difference is that primary memory is also known as main memory, this we mentioned earlier, or internal memory. And the secondary memory is also known as external memory or auxiliary memory. The last difference is that example for primary memory or RAM. RAM stands for random access memory, and ROM stands for read only memory. Remember, RAM is volatile memory. That means the data will be erased once the power goes off. But ROM is a non-volatile. Though it is a non-volatile, it is called primary memory because it is used, its capacity is very less, and it is programmed. And read only memory, you can program it only once, you can write only once. Of course, there are so many variations it in, like programmable read only memory, erasable programmable read only memory, PROM, EPROM. There are so many variations with respect to ROM, but remember they are all programmed to be execute or perform a single task repeatedly. So these are used in dedicated electronic devices. And the example for primary memory is cache memory. Cache memory is a special type of memory. The goal of a cache memory is that it uses the frequently accessed data. The cache memory is used to store the frequently accessed data. So how can we know that, how can the processor knows that this type of data can be used frequently? For example, if you try to access an array, you expect that you access all array elements, and so all array elements can be, once you try to access the first element in the array with an expectation that you access the entire array elements, the entire array or all array elements, place all those array elements in cache memory rather than primary memory. So this cache memory resides in between main memory and this processor. Processor means CU plus ALU plus registers. So the goal of the cache memory is, remember this word, it is used to frequently access the data. So this is also one type of main memory. PROM, programmable read-only memory. EPROM, erasable programmable read-only memory. EPROM, double E, electrically erasable programmable read-only memory. And registers, all are said to be the examples for primary memory. And the examples for secondary memory is hard disk. Can be external hard disk or internal hard disk, floppy disk, magnetic tapes, or even CD, compact disc, DVD, digital versatile disk, or your USB drive, USB devices, pen drives, all comes under secondary storage devices. Next, we see how the computer memory stores the data and instruction. You know that computer memory stores the data and instruction. Memory system can be divided into four categories. These are very important. First one is register, CPU registers, which are very near to CU and ALU. The registers are smallest memory elements which are used to store the result, intermediate result. Second one is cache memory. I tell you, cache memory is resides in between primary memory and CU and ALU, and the goal of cache memory is to store the data that is frequently used in near future by the CU and ALU. And the next memory is primary memory or main memory, and the last one is secondary memory or mass storage.